Last week we studied the 3 different gas laws, Boyle's law, Charles' law, and Gay-Lussac's law, and their relationships qualitatively. So we did a lot of increase, decrease, as volume does this, what does temperature do? As pressure does this, what does volume do? So this week we are going to introduce some equations that will kind of support all of the relationships we talked about and observed last week. And these equations can be used to now quantitatively, or give us calculations to relate pressure, temperature, and volume. So the first law that we're going to talk about is actually called the combined gas law, because this is what we see in the real world. We talked a lot last week about how Boyle's, Charles, and Gay-Lussac's law keep one of the variables constant so that we can see the relationship from one to the other. But in the real world, most of the time, all 3 variables are changing at once. And that is what the combined gas law tells us. So this equation is pressure and volume and temperature of a system are going to be, just like we've learned, Boyle's law says that pressure and volume are inversely related, so those 2 are multiplied at the top. And then, and if you think about that mathematically, as pressure increases, volume decreases, so that it would be constant still. And then temperature is on the bottom because it is proportional or directly related to both pressure and volume. That would be the Charles and the Gay-Lussac law. And so this is supposed to be constant, or it will remain proportional in their amounts from any change that you might make. So in these examples, we're going to be looking at kind of a before and after of the gas. So that's why I put 1s next to all of these. But this proportion, or this relationship between all of them, needs to stay constant. So whether I change them, increase or decrease, this relationship should stay constant. So we're going to put them equal to each other, that it will always be inversely and directly related. Pressure to volume inverse, and then both variables to temperature, and remaining constant. So this is taking those kind of qualitative examples we talked about last week and now putting an equation to it. So when we're working with the combined gas law, in order to get any of the individual gas laws, all you need to do is cross out the variable that is held constant. Cross out the constant variable. So for Boyle's law, we know that the constant variable there is temperature. So if we cross those out, we are just left with P1V1 equals P2 V2. So there's our inverse relationship between pressure and volume, that they will, as one increases, the other will decrease. And mathematically, that's what will happen when we use this equation. Charles' law, that one holds pressure constant. So if you cross out pressure, we're left with V1 over T1 equals V2 over T2. And this should look similar to proportions, right? Proportional reasoning. We will need to, when solving these, to use cross multiplication, so that will be helpful. We talked a little bit about that on Friday, making sure that we all remembered how to do cross multiplication, and we'll touch base on that again on Wednesday. And the last one, Gay-Lussac's law, has volume constant. So if you cross out volume, you're left with pressure P1 over T1 equals P2 over T2. And again, this looks like a proportion because when things are directly related, they are proportionally written in an equation like this. So 2 more important pieces of information that we need when solving these. Sometimes it'll just say a gas at STP, like example 1 says that. So there's some important information that can tell us, and it actually tells us a lot of information because STP, as we've talked about before, that's standard temperature and pressure. So that's giving us both the temperature and the pressure with various units because we know what they can be. Pressure has lots of things at standard pressure in various units. The most common one is 1 atmosphere. That's what we learned first. But then we've also listed some new ones last week. So we've got kilopascals, that's 101.3. If we're going to do torr, 760, and that's the same as millimeters of mercury, and it's 14.7 psi. So there's all the different pressure units that you could possibly use. Whichever one you pick, that is what your final pressure unit will be in. So if I choose, for example, 1, if I choose atmospheres, which I think I will do that when we solve it, then my answer is also going to be in atmospheres. If you plug in 101.3 kPa for your pressure, then your pressure 2 will also have that same unit. So just keep that in mind when you're solving these. Pressure 1 and pressure 2, or really any of the variables 1 and 2, will have the same units and need to be plugged in with the same units into the equation as well. Temperature at standard conditions is, the first one we learned, 0 degrees Celsius. That's also 273 Kelvin. And Kelvin is what we will always use to plug in for our temperatures in these gas law problems. So just a little note here to remind you, add 273 and you will get Kelvin. And that's 2 degrees Celsius. If you're curious, I don't think I give you any in Fahrenheit, but you can always convert if you are given Fahrenheit. It's kind of a weird conversion. 9/5 times the degrees Celsius plus 32. So there's our conversion to degrees Celsius if you were curious. But again, I don't think that is going to be necessary for our problems, at least today. The last vocab term we're going to talk about is Kelvin. And Kelvin is our absolute temperature scale. And when I say absolute, that's just meaning it is 0 means absolutely 0. There is no negative value. And Kelvin scale is measuring the heat or the movement of the particles. So when there's no more movement, that's where we're at 0. And I think we've talked about this before, that 0 Kelvin is nearly impossible. Dare I say impossible? There's always possibility, I suppose. But up until now, it is impossible because by simply observing any sample, you're putting energy into the system and putting just a slight amount of heat energy into it just by your presence. So we've gotten close to 0 Kelvin, but not quite there in observance in lab or even in outer space. But my big point here I want to say is that, absolute temperature scale, that means there's no negative values. And we always use Kelvin in gas law problems. So always add 273 if it's in degrees Celsius. Always, or you will get the wrong answer. That's very important. Okay, so excuse me. We're going to do some examples of solving these. And just a couple of tips before we go into that. I already said that your units for kind of variable 1 and variable 2, if we're talking about pressure, they have to be the same. So if you use atmospheres for P1, then atmospheres also needs to be P2. If they are given in different units, then you need to convert them like we did last Wednesday before solving. And the same applies for volume and temperature. Make sure they're the same before you plug them in. Only use Kelvin when plugging in for temperature, and if you have proportions, go ahead and cross multiply to help you solve them more easily. So for each of these examples, we are going to circle the given value and determine whether each is a volume, temperature, or pressure. And then we're going to identify the corresponding gas law, predict what will happen to the gas, and write the equation. And then that should set us up to solve it really easily. So we've got this example, 1 liter of gas at STP is compressed to 473 milliliters. So I'm just going to circle all of my given values. And this is a volume, so that's volume 1. This is actually telling us temperature and pressure. So we'll have to look at our question at the end to decide which one is going to be important. This is also a volume. This is the volume at the end, so volume 2. Now, right off the bat, I'm seeing different units. So I'm going to change this into liters really quickly. So we're just ready to rock and roll. Remember, milliliters can be changed to liters by dividing by 1,000. Then it says, what is the new pressure? So since we're going to be looking at the relationship with pressure, we're going to only care about the pressure from STP. So our relationship here looks like we're doing volume and pressure. Which gas law is that? If you said Boyle's law, you are correct. So it says, will the pressure increase or decrease? Well, our volume is going down. According to Boyle's law, our pressure should go up, because as volume decreases, pressure increases. That's what we did last week. So our new stuff, our equation, we've got Boyle's law is P1V1 equals P2V2. Let's go ahead and plug in our information. We said V1 is 1 liter. Oops, sorry, that's V. P1 is our standard. So we have lots of different units to choose from. I'm going to use 1 atmosphere. And then I have my V1. And then I've got P2 we're solving for, and V2. Make sure you use the one that's in liters. Same units, so important. Now we solve for P, so divide. Use those math skills. So we got P2 equals 2.11 atmospheres. And we're rounding to 3 significant figures in this one. So 2.11 atmosphere, and that went up, just like we predicted, from 1 atmosphere to almost double, or actually a little over double. Okay, example 2. Ooh, excuse me. Let's do the same thing. Let's circle our given values. We've got 3 given and 1 we're finding. So this is volume 1, temperature 1, volume 2. I bet we're finding temperature 2. Yep. What temperature? So that would be T2. Volume and temperature is Charles' law. Okay. Our volume is going up significantly, so that means our temperature is also going to be going up. This is our relationship from last week. So our new equation here, we got V1 over T1 equals V2 over T2. Make sure your Celsius is added to 273, so it's in Kelvin. And then plug and chug. Your answer should have 1 significant figure. You do the work, but there's your answer, 50,000. And I'm going to have you do example 3 on your own. Do the same process, and we'll go over that together in the Zoom.